Okay, so what we're going to do is we're going to practice one more of these simple iterated integrals, and then we'll start practicing how do we, if we choose to switch the order of integration from, say, dx dy or to dy dx, how do we go about doing that? So, but let's do one more of the problems where they're, in essence, telling us the setup that they want us to use. So let me read. So we want to use an iterated integral to find the area of the region bounded by the following graphs. So obviously, if f of x equals sine of x, this is basically saying y equals sine of x and y equals cosine of x. Now that's exactly what you're seeing here. So this is, we have the cosine curve here, the sine curve here. And if it's bounded from, or bounded by these two regions, clearly depending, we'll have to get to the x part first, because as you can see, depending on where we, what x values we choose, it's possible the cosine curve is above the sine curve or the sine curve is above the cosine curve, right? So that would change where, if we're going to place sine in the upper bound or cosine in the upper bound, right? It just would depend. Well, so we also know that this curve is bounded between x equals pi over 4 and x is equal to 5 pi over 4. So that gives us all the information we need. So now we know that we have some vertical lines here at pi over 4 and 5 pi over 4. And in essence, we're trying to find the area between these two curves bounded on each side from pi over 4 to 5 pi over 4. So that is what allows us to figure out the region that we are looking to find the area of. So now it should make sense that, so let me start with just a generic double integral here. And recall that we want the constants to be on the outside, right? So since the constants deal with the x values, we definitely want to perform integration with respect to x last. So we want dy dx. Now we can go ahead and fill in for the x values. So we're going to be going from pi over 4 to 5 pi over 4. This next part, whether we put sine here or cosine here, again depends on the x values we chose, because as you can see the cosine curve is above the sine curve at intervals, at other intervals. So because we chose from, or it was chosen for us from pi over 4 to 5 pi over 4, the upper curve, right, it's bounded from below sine and above cosine. So below sine, above cosine, meaning we want to integrate from cosine of x to sine of x. All right. Now again, there is nothing to the integrand for now. We can just assume that it's 1. So if we integrate 1 with respect to y, let me go ahead and start to write this out. We integrate 1 with respect to y is just y. I'll try to pick up the pace a little bit. So now we'll do f of sine of x minus f of cosine of x. So that gets us to, and I don't want to forget my dx. So pi over 4 5 pi over 4. All right, so plug in sine of x for into y. Again, if we integrated with respect to y, we want to plug in to y. That didn't really matter here because there is only one variable, but again, just to make sure you keep your work neat. Now we'll do minus the lower bound, which is cosine of x. And we still got one more round of integration that we're going to do with respect to the x variable. Okay, well, if we integrate sine with respect to sine of x with respect to x, we get negative cosine of x. And if we integrate, so if we integrate sine, we get cosine, so this should be minus sine of x. Sometimes I can talk myself out of things. All right, and then one more round of back substituting. 5 pi over 4, f of 5 pi over 4 minus f of pi over 4. And we end up with an area of 2 square roots of 2. Okay, so not bad, not too bad. So I'll reiterate one more time. The order in which you do dy dx does not affect the solution, but it does. It can affect the ease of the integration process. In fact, there are some problems that may be unsolvable if you integrate dy dx, but solvable dx dy. Okay? So let's go ahead and read the next example. So we're asked to sketch, we want to sketch the region whose area is represented by the following integral. Let's start there. Okay? So let's we'll start, it doesn't matter to me if you want to start on the outer integral, the inner integral. So the outer integral is dy, so that would mean the way you would interpret that, 0 to 2 dy, just simply means that we have horizontal lines at y equals 0 and at y equals equal to 2. Then if we want to interpret the integral from y squared to 4 dx, again, we're just going to interpret that as x equals 4 and x is equal to y squared. We'll start with these horizontal lines. Those are fairly easy. So I'm going to draw a horizontal line at y equals 2. And I'm going to draw a horizontal line at y is equal to 0. All right. So I know that the region I'm interested in finding the area of is going to be bounded from vertically from 0 to 2. Now, horizontally, we know that there is a vertical asymptote at 4. All right, so this is x equals 4, y equals 2, y equals 0. And then, of course, we also want to graph x is equal to y squared. Well, we know that when the x variable is squared, the parabolas take on one of the two following forms, right? But if the y is squared, then the parabolas are going to take on one of the following forms. Okay? It just so happens that since the coefficient in front of the y squared is positive, the shape is going to take on the following form. So I'll try to graph that. Let's see here. So looks like this. Sorry for my my beautiful artistic ability here. Good enough. Good enough. All right. So what does that look like? Well, so we are interested in the area bounded vertically from 0 to 2, and then bounded horizontally from y, basically below, or we could think of it from y squared to 4. So this is the region that we are interested in finding the area of. Now, we could continue with this integration process, but that's not really what I'm interested in right now. So we've already practiced this part. What I want to practice now is, what if we switch the order of integration? What if we switch to dy dx? The question is, how is it that we must change our bounds in order to reflect the change in order of integration? Right? Because you can't use these same bounds and just switch dy dx, dx dy. That's not going to work. We have to rethink about how it's bounded. So I kind of like to start with the outer bounds, because I know that they're going to be constants, right? So, and I'm going to use this picture as an aid. So if you don't mind, let me paint a picture for you. So let's assume that you're taking an exam or doing some type of practice problems, and you start off deciding to do order dx dy. Then you get to the part where you're about to start integrating, and you just run into some really heavy integration that you start thinking, well, man, maybe I can go ahead and switch it up to dy dx. So let's see what that integration looks like. Maybe it's a lot easier. So if you will trust me, if you will graph your region before you start doing your integration, if you will just plot out the region, you can then use this region to help you when choosing the new bounds. So for example, we know that constants need to be on the outer integral, and the constants need to be in terms of x. Well, looking at our plot, if we're going to think about our x values now, right? So our x values, if you want the same region, how would you think about that? Well, you would have to go from 0 to 4, right? That would, now we're looking left to right now. Okay, if you wanna bound it with constants from left to right, we would want to go from 0 to 4. Okay, so x is 0, x is 4. All right, so that keeps us in the same region. And now let's think about, well, how do I change my my bounds for integrating with respect to y? So what you want to do is you want to grab the y squared. So originally we had x is equal to, well, actually I have it written down at the bottom, so let me just use that. So originally we had x is equal to y squared. So you want to solve that for y. So that would mean that y is equal to what? Plus or minus the square root of x. Now, we don't need to worry about the negative, but listen, let me just put it this way. If you were to graph the square root of x, that would look like this, right? That gets us this top half of this parabola. If you were to graph the reflection of that, that would get you the bottom half of that parabola. Okay, so I will go ahead and plot that. All right. And now we need to think about, what does, so let me see if I can explain it this way. So if you were to take this 0, when x is, or let me say it this way. So if you think about x being 4, or let me put it this way. If you take 0, plug it in for y, 0 squared is 0. If you take 2, plug it in for y, 2 squared is 4. So in other words, when y is 0, x is 0. When y is 2, right? Or I put it this way. So when my sincere apologies, it's getting late. So I think you get what I'm trying to say, right? So we can, in other words, we can use our bounds to finish this up. So what should that look like? Well, that should look like, so y is obviously, so now do me a favor, let's look up and down, not left to right. So you still want this same region in here. So looking up and down, what are the bounds? How do we think about the bounds so that we are in here? Well, we need to be above 0, and we need to be below the square root of x. Does that make sense? If you're above 0 and you're below the square root of x, that will get us the region that we want. So, in other words, we want to be going from 0 to the square root of x. This will take a little bit of time. It will. If you want to think about graphing y equals 0, y equals the square root of x. The goal is, but do you see how it's so much easier to get from one to another if you just take a second and plot it out, right? Just trust me, I promise you'll get better at this, but you just got to get your hands dirty, okay? You just got to get into some practice problems. Okay, but this, whether we, and on your own time, you can integrate either one of these or both of these, but either way, the area of these regions, areas of each of these, is 16/3. Okay. So I hope that helps a little bit with the way that we're switching from dx dy, dy dx. We will practice it a little bit more. The last thing that I want to do is again, we're just going to practice the setup, not the whole integration part. But what if I give you a graph, something like this, and I ask you to, I could do one of two things. I maybe on a test, I give you a graph like this. I might ask you to find the area. And if I were to ask you to find the area, then it would be up to you whether you do dy dx or dx dy. It's also possible that I give you a graph and I just simply to ask you to set up both dy dx and dx dy. In that case, I probably will not ask you to finish it. I just want to make sure, I just want to see if you can set it up. So let's start with let's start with the first graph, right? So clearly we're trying to find the area of this region. We must use a double integral, right? We're not just using length times width formulas in Calc 3. And let's see, how would we set up dy dx? How would we set up dx dy? I think what I will do is, since it's getting late, I'm losing track of time. I can't remember how long I've been recording. So I think what I'll do is I'll do this first one, and then I will include this second one in the next video, probably like a warm-up for 14.2. These are the last two problems from 14.1. Okay, well, let's go ahead and let you and I agree that for the first graph, x is bounded from what? Well, it's bounded from 0 to 8, right? So x is bounded from 0 to 8. Y is bounded from 0 to 3. So this is fairly easy because see how all you have is constants for your bounds. So that will make it easy when you switch it up going from dx dy, dy dx. But if you want to do, just again, make sure that if you want to do dy first, that is associated with the bounds for y. Okay, if you want to do dx first, just make sure that's associated with the bounds for x. But after you're there, well, let's go ahead and plug it in. So dy first, that would mean that it's bounded from 0 to 3. And then obviously dx would be the last integration. That would be bounded from 0 to 8. And if you want to switch that up, that's quite easy. You just need to, now that you're going to integrate with respect to x first, you want to make sure your bounds 0 to 8 are on the inside. And then, of course, integrating with respect to y, you want to have your bounds 0 to 3 on the outside. Okay, so if you would like, if you are feeling awake, maybe you've had some coffee in you, if you'd like to try just the setup, dy dx or dx dy, you don't have to finish it. You could try it and see what you get. And I will see you guys in the next video.